Evening and welcome to the Day 5 Session-9 of ATAL Online FDP on Quantum Intelligence, Integrating Quantum Technology with AI and ML. Today's first speaker is Dr. Shubhasree Chatterjee, and the title of his presentation is Quantum Sensing and Measurement through AI. The session spans from 6 p.m. to 7:30 p.m., including all interactions from the participants. Dr. Shubhasree Chatterjee is an accomplished researcher specializing in advanced materials and photonic devices with over 10 years of experience in academia and industry. He currently serves as a research associate at NTT BRL, Entity Corporation in Asugi, Japan, focusing on quantum 2D heterostructures, ultra-fast optics, terahertz dynamics, and photodetector development. Previously, he worked at the National Institute for Material Science at Tsukuba, where he specialized in the synthesis and application of 3-4 colloidal quantum dots for infrared photodetectors. Dr. Chatterjee holds a PhD in engineering from Hokkaido University and a Master of Engineering from Shizuoka University. His research has been published in leading journals such as Nanoscale Horizons and ACS Applied Nanomaterials, and he has presented at numerous international conferences. He is skilled in nanomaterial synthesis, device fabrication, and advanced characterization techniques, including XRD, TEM, SEM, and ultrafast spectroscopy. Dr. Chatterjee is also a recipient of multiple awards, including the Best Presenter Award at ICNERE 2018. May I request Dr. Shubhasree Chatterjee to start his session?
Thank you very much for the introduction. Am I audible to all?
Yes, yes, sir.
Okay, so thank you, madam. So I will start to share my screen. So is it okay? Can you see my slide now?
Yes, sir.
Yes, sir, it is visible.
Okay. Okay. Thank you very much for the introduction. My name is Shubhasree Chatterjee, and I work as a research associate at NTT. And today I'm going to talk about quantum sensing for ultra-fast photo detection and application of AI. Um, and thank you very much to the organizer for inviting me to speak about some of my research. So basically, I want to introduce the company. Entity is a telecommunication company, and the R&D section is in Atsugi, Japan, and it has um, a lot of other companies. Maybe Docomo is widely known in India. And in our basic research lab, we are in the quantum solid state physics research group, and currently we are working quantum Hall edge state, topological insulator, and some flying qubits, and some other material heterostructures to have some application in terahertz and terahertz photodetectors and many electronics applications. So basically, we also work in like superconducting qubits, topological qubits, trapped ions. All these have application in quantum computers. So people like companies like Google or IBM or Microsoft, they are developing these quantum computers, making their processors and cheap. But many startup companies and many other companies also focusing on developing only some of the parts of the quantum computer, not focusing on the whole computer. So we are one of them, and we are also working. We have a lot of dry fridges, refrigerators like this, and we can cool down to millikelvin range, and we can have the superconductivity with various metals, and that's kind of a work we do. And at the same time, the other subgroup where I belong, we work on quantum sensing for ultra-fast communication and detection. As I said, this is a company um, for telecommunication. So obviously, for communication, we need to, as the data traffic is increasing day by day, we need to have very fast communication, and for that we need some noiseless photodetectors and sensing techniques to improve the detection efficiencies. And a lot of scattering, a lot of errors are there, so we have to somehow improve the efficiencies of the detectors, just like introducing some materials into, like from quantum dot to 2D material or some other material. And some of the application we can do is in the infrared imaging or terahertz imaging, and I will introduce the application areas. And like single photon detection for the application of quantum secure communication, leader application, and also for next generation ultra fast photo detectors to have the conversion optical to electrical with higher efficiencies. And recently, like 5 to 8 years ago, this Moire structure with 2D materials are um, started to introduce in the research community. So currently, this Moire structure is also one of the um, like potential candidate to have single photon detection from photodetectors, even for superconducting qubits and all. So one by one, I will introduce, and I want to acknowledge my team from Entity, and we collaborate with Professor Vasily from University of Buffalo for the theoretical calculation. And also I have worked at NEAMS with my some of my colleagues and Professor Shirahata, and also we have collaborated with Professor Batu Ghosh from Raniganj College, Bhalotia College. And I want to acknowledge some of the grants like JSPS Kakeni and Eloquent projects to um, sponsored our work. And so basically, quantum sensing is very important, as I mentioned, that for ultra fast communication and detection. And so the data traffic is increasing day by day, population is increasing. So we need more faster communication, and we need a lot of more storage in the data centers. So in this case, if we just substitute the conventional detectors, conventional devices with some quantum devices, and also if we improve the sensing technology like quantum sensing, then we can extract a lot of physics, and then we can, at the same time, we can improve the device structure and device efficiencies. So photon detectors is one of them. And photon detectors has this kind of application, as I mentioned already. So basically, to understand the process, we have to understand how the process start actually. So basically, we do material growth or synthesize a material by using CVD or MBE technique, like epitaxy molecular epitaxy or CVD deposition technique. And then after making that, we characterize all these materials, like the properties of these materials, how it works under X-ray or infrared, and then after knowing the characteristic, we fabricate, and then after the fabrication, um, we measure according to our application. So for, let's say, for telecommunication, we need very fast signal to transmit. So on that case, if we just measure the photo detectors in time domain and convert to the frequency domain, then we can have a 3 dB bandwidth like this, and then we can say the bandwidth of this signal and of this device and how fast this device is working. And the mechanism of a specific device is also very important to understand. For that, we need to do some kind of um, dynamical study of the device, and how this dynamical study often do, like if we shine a light, and after shining a light, the atom will absorb, and due to that absorbance, the atom will emit a photon, and after, with a delay in time, if we probe that signal, then we can understand uh, which mechanism is the source of this of working principle of this device. And this is the flow of the whole study, and how this AI could improve the sensing technique. So day by day, the devices are getting smaller, and so for commercial purpose, we need to have a very good signal to noise ratio. So for that, AI can help to improve the signal to noise ratio in this kind of devices. And also for the imaging devices like terahertz imaging or infrared imaging, AI can really improve the signal to noise ratio of the imaging part. So basically, what is terahertz imaging? Like, um, as this COVID happens, then we we know that we have a like wireless thermometer. It works like it detects the heat from the from human body. So generally, these infrared or terahertz detectors can detect the body temperature without touching it, and also it can be used as night vision cameras. And this terahertz imaging technology often have many direction, like optoelectronic terahertz imaging has used by pulse lasers, and or CW continuous wave terahertz imaging, and other also applications like in terahertz imaging, like passive terahertz imaging, active terahertz imaging. This kind of application for terahertz imaging are being researched. And for infrared, basically for infrared cameras are being used in army, specifically like when smoke gas blast, enemy people cannot see it. But if the enemy people, if the person wear infrared lens or infrared camera, then they can just understand the subject very clearly, even in the smoke or in dark field. So, which is the main advantage compared to the visible cameras. But the thing is, the commercially available infrared cameras are really expensive. Like it cost one camera, it cost like more than 1 million rupees, and it's very bulky and it's very big. So if we introduce this kind of quantum materials like 2D material or quantum dots, then what we can do is we can reduce the cost, and also at the same time we can reduce the size of the device, and it can be useful for not only for the army application, of course, for the space application, or like NASA has these kind of infrared cameras, or for the leader application, like new smart cards are introduced by many companies. So this leader application is really important. If we integrate with AI, then we can sense how much distance is there in between two cars, and this kind of application is very new. And here you can see that when the light is on, when we are using red, green, blue RGB cameras, we can see the person. But in thermal camera, when the light is on, we can see him by this. And if we switch off the light, still we can see him by using these thermal cameras. So the main advantage is it can be useful for this kind of situation. But how this works, that's main physics. And because the material we are using, it absorbs the infrared light, that's it. So we have to search the specific material for specific application. The material which absorb for infrared, it can be useful for infrared cameras. The material which can absorb or emit in terahertz range, it can be uh, useful for that application. So single photon detection is another application area. Um, so what is single photon detection? So when we pump a light to a material, what happens? When we introduce a light to a material, the electron um, get absorbed, and then it goes from valency band to conduction band, right? And then after releasing the energy, it releases a photon and then comes back to the valency band, right? So when it release, if we use some kind of detector which can sense a single photon emission at a time, it will be useful for the application of quantum information, right? So these kind of detectors should have very low noise, and that low noise is possible when um, there is no defect on the material. Often when we synthesize or we grow the material, we have a lot of defects. Also, I mean, for the application of different genre, those defects can be useful, but sometimes it also, for this kind of application, it is not a good idea to have a defect. So we have to prepare a very good material first of all, and then we have to choose the material, and also we have to choose this incident laser wavelength which it absorb. Like the material which absorb infrared, then we have to choose an infrared laser, or visible for the visible one. So this kind of single photon detector SPD photodiodes are already available by Thor Labs and some other big companies, optics companies. And so these kind of single photon detectors often used in photoluminescence measurement, like the people who works in LED, like light emitting diode, they measure the emission quantum yield of the material by using photoluminescence. They shine a light of the material, and but that material emits, and by this kind of detector you can have the emission efficiencies, and then you can use it for LEDs. Nowadays what we see in organic LEDs or LED TVs, this kind of material are often used. So next generation quantum dot based LEDs are, I think, already introduced by Samsung, and it's really expensive compared to the one we have for like organic OLEDs. But the making cost of these quantum dots are really low. But the problem is the measurement techniques needs to have a lot of state of the art facilities. That's why the fabrication cost and the sensing cost is really high. That's why um, the commercial products are higher nowadays. But I guess in future it will be very very low. And for the next generation ultra fast photo detectors, this can be useful for you know telecommunication. So for the telecommunication, uh, we shine a light to transfer the signal. We shine a light by a LED or a laser through optical fiber, and what we get optical signal to a detector, and that detector convert the incident optical light to electrical one. That's the basic function, optical to electrical. But the conventional photodetectors like PN junction based photodetectors, they have the working principle with drift and diffusion. And by introducing P and N junction, we break the symmetry by um, introducing applied voltage externally, and a building potential introduced, and then the current flow appears. The problem is the photo response speed and the efficiencies are very very limited, and the photocurrent generation at 0 volt is really important, because what we do is to have a built-in potential of this kind of devices, we apply some voltage externally like plus 1 or 10 whatever. So when you don't shine a light in the dark condition, due to have the external voltage, still a dark current always flow in between the device, which limits the efficiencies. So what we need for next generation photodetectors, we should have some 0 volt photocurrent generation mechanism in a device. That's kind of a challenging. Um, so on that case, what you have to do is specifically you have to choose a material which can have the symmetry broken condition without applying any external voltage. And other limitations like frequency limit, that has been done by band gap of the material. Conventionally, silicon and germanium are widely used, and I think infrared photo detector cameras, indium gallium arsenide based photo detectors are available commercially. So that's why we need to have some new material, new photocurrent generation for improving the efficiencies. There are that These are the important factors to have ultra fast photo detection. So when so uh, what are the steps to collect the photocurrent at the electrode? As I explained, when we shine the light, um, electron moves from valency to conduction band, and hole generate at the valency one, and it makes a exciton, and if we and after a few time, these electron, they release their energy by electron electron or electron phonon um, scattering, and they comes in the lower of the conduction band. After that, they comes back to the valence by releasing some energy, and then we get this photocurrent. So this is a specific way, and when we shine the light on the material, uh, initially electron gets hot, and then it thermalize within very small time, like femtosecond level. And after few femtosecond to nanosecond level, it releases the energy, and then we get the signal. Now this time scale, time scale in nanosecond or picosecond or femtosecond, which is very very fast, right? So to get that signal that fast, we need to have that kind of electronics, that kind of measurement techniques, that kind of machines which can detect all these kind of phenomena, right? So that's why quantum sensing techniques are really important to understand the carrier dynamics of a device, because these carriers releasing their energy, thermalizing their states within femtosecond to nanosecond. But conventional materials, so conventional photodetectors, often has photoresponse in nanosecond to millisecond range. So if we want to make that picosecond or femtosecond, then we should have uh, the electronic system. We should improve that, and also at the same time we should understand what is going on, why this is so fast, and how we can improve the sensing techniques. So there are a lot of quantum sensing techniques available, like photocurrent spectroscopy. If we scan laser through through a material X and Y direction, then we can image a DC photocurrent, which is um, uh, um, which doesn't move actually, and which is a DC photocurrent. But if we shine a different polarization of the light, like linear or circular polarization of the light, then we can also understand the current generation, whether this is a non-linear phenomena or this is just a photovoltaic boring effects, which we often observe in photodetectors. And also, if we change the direction, we can have spin photodetectors for applications like memory devices and all. And we have other quantum sensing techniques, like ultra-fast autocorrelation. We shine a light with laser, and with a delay, with the same laser, we probe it, and we see the change in the absorption of this material locally. And other techniques like NV center diamond spectroscopy, and some other techniques I will explain here. Like this is DC photocurrent photocurrent sensing technique. We shine a laser X and Y direction on a material, and then we can have this photocurrent. And some other technique, like if we have some quantum material like graphene, is very widely known popular material. And if we have this kind of graphene or like 2D other 2D materials, and if we use some kind of tip with a AFM and with a tip, and if we scan throughout the material, and then we can have this kind of photocurrent imaging. And these DC photocurrent imaging we can achieve, but it doesn't give you any information about the carrier dynamics. That's why the time dependent photocurrent spectroscopy is important. And on that case, if we use some on-chip ultra-fast photocurrent detection, uh, like these and these, then we can understand the dynamics of the carriers, and it will flow through the waveguide. Then what we can understand the transfer characteristics of the photocurrent. Now we have complete scenario. We can understand the dynamics, we can understand the generation phenomena, and then we can make this technique as a photo detector, and we can produce very fast, ultra fast photo detectors for next generation. So, and how do we understand the generation mechanism or the dynamics? We change the temperature, and by changing the temperature from room temperature to cryostat temperature, like 4K or 10K, the dynamics will also change, because at the low temperature the scattering will be less. Scattering means this kind of scattering. When the carrier release their energy, the scattering will be less in low temperature, and high temperature different scattering like electron phonon becomes more higher. So if we reduce the scattering and we measure all the photocurrent in low temperature, then we can have some kind of idea what is going on and what is the generation mechanism, and then we can produce a device which can be faster. So these are the techniques usually um, often used for detecting the photocurrent. So these are uh, scanning photocurrent, DC photocurrent imaging technique. These are steady state photocurrent actually. These are not time domain. So for the time domain, the autocorrelation and NB center photocurrent magnetometry. So we have a diamond and we shine the light laser to a diamond, and after a few time we probe with a microwave or other laser with a time delay. We can check the photocurrent on that location. So all these two time domain technique only can probe locally, not non-locally. So we need to have an understanding for non-local phenomena. So this on-chip spectroscopy, uh, it can give you on non-local photocurrent generation and their transport characteristics, and at the same time it can give you a complete photo detector. And the time resolution is also important. As I said, the releasing of the energy and the thermalization of the carriers, everything is happening within femtosecond to nanosecond or picosecond level. So we need to have this kind of fast photo detection technique, quantum sensing technique, to extract the signal. So this is the two difference for the local measurement and non-local measurement. We shine locally and we absorb what is happening locally, but when we do the non-local one, then a photocurrent generate and it can flow from source to drain, and then we can extract the signal from either electrode. And this is kind of on-chip photocurrent technique. We excite here in a 2D material, and due to that excitation, a terahertz photocurrent generate. And we excite with a pulse femtosecond laser, which has a pulse duration around 280 femtosecond. So for that, terahertz photocurrent with the ultra fast signal appear, and then it flows. So some people are wants to join. Okay.
Hello, sir. I
Um.
have a question. May I ask now?
Please. Sure. Sure.
Yes,
Sure.
sir.
Please go
Because
on.
I have
Yep.
some doubts actually. Sir,
Yeah. Please
first
go
thing
on.
is that we are talking about photo detector. As you started, you said that we are having photo detectors. We are using these photo detectors in optical fiber communication in order to convert our optical signal into electrical signal, right? So what is
Yes.
happening? Photons are falling on the photo detector, and a photocurrent is generated, right? That current is
Right.
basically converted into electrical signal using electronic circuitry, right? That happens in our simple optical fiber communication. Now you are saying that quantum sensing you are relating with the photocurrent generation, and somewhere you told that we are having the transition and the current is generated and the process is taking femtosecond and femtosecond or whatever less time. So that point I am not clear where you are talking about this femtosecond point or less time. That I am not clear. What is that time?
So yeah, so basically what we see in a normal photo detectors, so we stack different layers of materials, right?
Yes.
Like you have a substrate, and then um, you introduce one electron transition layer, and then you have an active layer, and then you have a other layer, and then you have electrodes. And
Correct.
if you shine the light on the active layer, then a
Yes.
photocurrent flow from one electrode to another electrode, right?
Correct.
So these
Correct.
are techniques for these are the techniques usually are for extrinsic phenomena. What we observe for normal detectors is extrinsic phenomena, but the thing is intrinsic phenomena. I'm talking about the intrinsic phenomena of that material, of that active layer. I'm not taking care of other layers. So what is
Okay.
happening on that active layer is very important to understand. That's the physics. Now, if we improve the efficiencies from the active layer, then we stack with other materials, then we make our devices long, or we integrate with other thing, then we can easily improve the efficiencies. Usually, for the photo detectors, what you see in normal, like this. So for this kind of photo detectors, you shine a light on the active layer, right?
Yes.
And then electron and hole generate. And then
Yes.
electron goes one side and hole goes other side. And then you have a
Correct.
photocurrent, right? So
Correct.
this is a technique for extrinsic phenomena. And this kind of extrinsic phenomena, often, you can see many papers are talking about that. But the thing is, what is happening only in active material, when you don't have these or these layers, only a substrate,
Okay.
and you
So we
shine
are
a light
talking
on the
about
material.
intrinsic layer. We are talking about the
Right,
I layer,
right.
P and N
Yeah,
layer. We are not talking. So in that,
yeah.
actually, when we are shining the light, then there will
Mm,
be photocurrent generation. That
right.
process is very fast. That you want to say?
Yes. Yes,
For,
and
so
that
that is
process, yeah, that process is really fast. And now that releasing the energy is really fast, like in femtosecond or nanosecond level. So you
okay.
should have, electronics, like we use lock-in amplifier, or like normal DSO.
Yes, a
So
receiver
this kind of
circuitry we
machine,
should have.
receiver
Yes.
we yeah.
Yeah.
So but these receiver circuits are not so fast. These thing cannot give you in uh, you know terahertz or gigahertz, several hundred gigahertz response. So you have to understand the intrinsic phenomena first, then you can integrate the circuit with like other, electronics available commercially. Then you can, have a fast detection. So I will show that actually how we do that. So this intrinsic phenomena study is very tough previously, because these on chip techniques and these quantum sensing techniques were not available. Because we have lot of fast laser, pulsed laser, if we shine the light, we are using like 280 femtosecond laser. So when we shine the 280 femtosecond laser, obviously we will get a very fast signal, right? So for that, if we understand this decay like we shining here and a terahertz current generated. So this decay is very important. The time of this decay, if we understand and we compare the mechanism with available theoretical mechanism like photovoltaic or photothermoelectric or bolometric or nonlinear shift current, then we can understand how this photocurrent generation is happening on this device. And now if we integrate with some other circuitry, electronics, then we can have the signal, fast signal. So now this is a 2D material. We shine a femtosecond laser here, and the photocurrent travels on a waveguide, through a waveguide, and with the same laser, with a time delay, we probe the signal from this low temperature grown gallium arsenide photoconductive switch. So, and then we can have these kind of very fast signal from only this material. So this is for graphene, and these two are different area. And 5 micron means the size of the the active area, but different mobility was used. So different graphene mobility was used. So by changing the graphene mobility, we have different decay signal, different time. The decay signal is having in a different time. So now you can distinguish how fast the signal, and if this is within 1 to 2 picosecond time. Now you can say this is not coming from normal photovoltaic or bolometric effect. So this signal was recorded at 0 volt. So obviously 0 volt phenomena associated with photothermoelectric effect or nonlinear shift current effect. And if we convert this signal to frequency domain, we can have very, very fast signal, like in gigahertz level or in like 0.2 terahertz. And so if we introduce these 2D materials or Moira structures, like I will explain, stacking this graphene or other 2D materials with a little bit angle in between that, then we can have very, very fast signals, and we can have very interesting light generation photocurrent phenomena. And if we shine the light with different light polarization, then we can have application for valletronics as well. As like valletronics is a field. We have conduction band and valency band, and if we shine a light and electron goes valency to conduction, and then if we shine with this kind of light, circular polarizer light, then this electron will flow one valley to another valley, and it can be used for memory devices like memory transistors or this kind of devices. And I'll explain with nanocrystals also, like quantum dots. If we use as photo devices, photodiode, and we study extrinsic phenomena, then we can have a simple photovoltaic effects or photobolometric effect. So the 2D materials are really popular these days. Like graphene gets a Nobel Prize on 2010, and after that, a lot of research has been done with graphene because this is very fast. It has a ultra fast mobility. It is zero band gap material. So obviously the transition from valency to conduction will be very, very fast. And it is the strongest among other materials. But the problem is the absorbance of graphene is very low, and it is a normal Dirac cone, like it doesn't have any well feature. So that's why people are more interested these days with other TMDs or black phosphorus or other HPN for other applications like emission or detection phenomena. So we usually what we do is we use a PN junction, and we apply a voltage and we break the symmetry, and then the photocurrent generation happen. And also in the case of magic angle superlattice, we stack same or different material and we make a tilt among them, and we generate a Moira structure, and then we can have a, we can break the symmetry, and then we can have a generation of the photocurrent. But recently, actually in the 1980s, there was a theoretical study that shows that if we use a material, a homogeneous material, which has some kind of symmetry already broken, like time domain symmetry or time reversal symmetry or rotational symmetry. And if we shine a light and at 0 voltage, it can have a photocurrent. And that photocurrent can be very, very fast. The efficiencies will be unity. So what are the limitations we have, or the, we can cross it easily if we use these kind of quantum materials. So that's kind of a hunt for uh, these kind, what are the materials we can have and we can study. So usually for graphene, this kind of this is a conduction manner valency band, and this is Dirac point. This is the Dirac point, and the Fermi level is here. But for the other 2D materials like WT2 is a material which is a type 2 well semicone. um, so well semi-metal has this kind of uh, cone features, and if you change the density, carrier density, or if you change the temperature, the Fermi level of the material changes, and the position of the electronic position of this conduction and valency band changes, and it sometimes it merged. And WTE2 is a semi-metal, so when it merged, it have a point, and these points are known as well points. And these well points, if we shine around here or here in this condition, then we can have very um, asymmetric or new phenomena which hasn't been discussed yet. So WT2 is one of the modern and newest semi-metal, well semi-metal. I think 10 years ago this material was introduced in Nature paper, and it has a phenomena that um, if we shine the light on WT2 on the lower symmetry axis, we can have a photocurrent on these axes. But if we shine the light on higher symmetry axis, the bulk part, the photocurrent will be absent. And because the reason is it has a circular rotational symmetry broken on the lower axis, and on the higher axis it constrains the symmetry, and that's why the photocurrent doesn't appear. And if we check the band gap, then we can see a lot of spaghettis like this, and sometimes we can see these points from here, and these are the theoretical calculation of the material. But if nowadays we can see these, we can image these band gaps via different quantum sensing techniques such as ARPES, angular resolved photon spectroscopy, photo emission spectroscopy. So these are the techniques which can image the the band gap of the material, and by changing the temperature, we can we can see how the band gap is changing. By changing the temperature, the band gap also changes, and we can image that. So these are very sophisticated sensing technique. And so recently, one paper, they use this special photocurrent measurement with a continuous wave laser, and they see the photocurrent appears on the edges. And they said that because on the edges the symmetry is broken, this photocurrent is appearing from nonlinear photocurrent. So another paper, they use NV center, diamond NV center quantum sensing technique, and they use a CW laser, and integrating with the spatial and photocurrent direction mapping, they say that this is coming from photothermoelectric effect, and that makes a controversy. And they are saying this is non-linear shift current, which is which has a potential to have very fast sensing, and they are saying this is just a photothermoelectric effect. And why is that? In this paper, they don't get provide lot of proof. They just use the CW laser and scan over the material and have this kind of photocurrent, and they just simply said that this is non-linear effect. But here they use they shine the light, and they said that when you shine the light on a material, due to shining a laser, it can have a heat, and this local part will be very hot, and along A and B axis a temperature gradient will appear, and due to that the electron will go from hot to cold region. So that means the photocurrent will go opposite of the electron direction. So the axis which has lower CVAC value, like that axis will have a photocurrent incoming, and the other axis will have a outgoing. And due to that, a forefront photocurrent appears on bulk. And these two photocurrent along two axes has equal and opposite photocurrent, and it cancel each other. That's why we cannot see any photocurrent on bulk or higher symmetry. But when we shine the light on a lower symmetry like this, like some angle, like some edges, we can have a photocurrent, because here there is no other the direction of photocurrent appears. The symmetry is broken. That's why we can see a photocurrent. So this is simply because of temperature gradient introduced photothermoelectric effect. This is not for non-linear photocurrent effect. So we thought we can, if we study the ultra-fast time domain photocurrent study by using this on-chip terahertz spectroscopy, then we can understand the dynamics. And for the nonlinear photocurrent, this conductivity is in a second order. So it follows nonlinear effect. Like if we increase the light, the shift vector increases with square root of that value. So it doesn't show any linear scale. It increased first and then it saturate after a certain point. So in this case, the photocurrent actually is shifting in momentum spectra, not in K spectra. So that's a difference. And this bulk photovoltaic effect is can appear only in homogeneous material without any applied voltage. So that's a kind of a advantage. But in the case of photothermoelectric effect, a CVAC effect, due to incident light, temperature gradients generate, and due to that electron flows from hot to cold region. And so as I said, we should have some kind of technique which can sense this fast signal, and that can say that this is coming from photothermoelectric or shift current mechanism. So usually what we do is mechanical exfoliation technique. We exfoliate the 2D material like scotch tape, and then we use a photoresist and spin coat, and then we make the laser lithography to make the electrode, and by evaporation technique we can just evaporate some material on the electrode and we can make the devices like this. And this is a glove box. We have to prepare all the exfoliation technique within the glove box environment, and if we do it outside, then some material is very oxygen sensitive, so the material properties can deteriorate instant. So that's why we have to use some kind of nitrogen or argon atmosphere in the glove box environment. And so this is a mechanical exfoliation technique. We put a material on a scotch tape and then we just fold it, and then we make this kind of first we fold it and then we strain it, and then we can have different layers of that material. And then after doing this method for 5 to 10 times, then we can have very thin 2D materials. And this is the technique used when graphene was discovered by a person. He was just randomly tries this method and it appears and he got the Nobel Prize. So it's a big advantage, because achieving the single layer of 2D materials by using the growth technique like CVD or MB is really tough. And I think for graphene, I think CVD is available but for other materials, it's really tough to have monolayer or very thin layer, right? So after exfoliation, this is very easy and fast technique, and anyone without any training can do that. And after exfoliation, these are the 2D materials. It shows that lot of small pieces we have, and you can just randomly choose you know your favorite thin flake from here, and you can just make a device and you can study the properties, and um, then you can have the applications. That is kind of a um, you know process in research level, but for commercial purpose this is not a good idea, right? So we need to have a very plain and very less rough material surface. So nowadays exfoliation techniques are also getting improved. So the researchers who are focusing on study the physics, they are just doing this exfoliation technique, and others trying to improve this exfoliation techniques with more cleaner surface. And we after exfoliation we choose a material, we choose a flake, and then we do AFM to understand the thickness of the material, and then we do the Raman spectroscopy to determine the axis. Like if we let's suppose take this material, take this flake, and if we shine a Raman laser here, then we can understand the axis. Maybe this is A, or this is B, or this is a edge in between A and B. Then we can just we can proceed for the fabrication of the device with this material, and then we can study the phenomena. And that's kind of easy, right? Yeah, but the physics is really tough, because when we have this material, lot of small flakes are there, and by understanding the visual contrast we can understand the thickness. So these are the blue, maybe these are the very thin, and these are dark blue, maybe the thinnest, and yellow and this green are very very thick. So if we uh, wants to have very thin material, we really have to check every flake from every chip, and that is very time consuming. And on that case, deep learning based automatic flake selection technique has been introduced. And if you just so these are the microscope we use to see the flakes, and we exfoliate on silicon chips. And if you just store the data, like the color of this material, and then it can work easily, it can determine by like this, and by checking the color resolution, the color contrast, it can determine the like your favorite thickness, and then it can just transfer on this, your uh, your chip, and then this process can be very automatic. So by using that, it will be very very useful, very easy to determine the thickness. And like this way, you have an input, and by using the interface the data stored, uh, it can easily tell you this is a 0.7 nanometer, which is like less than 1 nanometer, means in Armstrong level. So these are saying that this is monolayer, this is few layer, and this is thick layer. So you have to store the limit of the thickness. So if you say that until 1 nanometer it is monolayer, and 1 to 5 nanometer and this is bi-layer or multi-layer, it can show easily, and it can give you very fast result. And by using this technique, if you uh, also inform the color of the material, you can have the program can easily detect the nice flecks. And these are few other programs with integrates with the optical microscope. And all the programs, if you are interested, please check this paper. They have explained this phenomena, and they can easily detect the thickness of the material. So as I said, the people some people are trying to improve the efficiencies to sense this kind of materials thickness, and they are trying to improve the exfoliation technique. And if we collaborate with these people, and then we can have this easy technique to fabricate the device. And then we move forward with the favorite flake, and we pick it up, and then we make the device. So this is a on-chip photo detector device. So here we have, these are the electrodes, and we have the waveguide. So this is a simple gobo line waveguide. And this is a low temperature grown gallium arsenide photoconductive chip. And the specialty of this chip is, when you shine the light at 0 voltage, only then it open. So only then the photocurrent works. So this photoconductive chip was introduced by Bell Laboratory in 1970s, used to call Austin switch. So in telecommunication, these kind of Austin switch often use. And nowadays, gallium arsenide based photoconductive switches are really good, because they have very fast response. So if you want to probe the photocurrent in femtosecond level or picosecond level, then these kind of switches are really useful, because it it gives around 1 to few picosecond, I would say. And we connect with this switch with our fleck with a waveguide. And next, we our goal is to shine the light on the fleck, and due to that a photocurrent generate, and then with the time delay of the same laser, we detect the signal from here. And how and yeah, this is the response of a photoconductive switch. And this is the pumping, very small pulse width, as you can see, because we are using femtosecond to 80 femtosecond laser. And due to that, we can have a photocurrent like this in picosecond level or femtosecond level. And how do we distinguish the carrier dynamics? So for the case of nonlinear, pulse duration of the excitation light is very important. In this case, femtosecond. So if we got the result in if we get the decay of the photocurrent is in femtosecond level, then we can say this is nonlinear. And if we see the photocurrent is not changing by changing the temperature and all, then we can say this is because of the carrier decay temperature, which is related to the PT effect. So that's how we can distinguish this phenomena. And this is a measurement setup we use. So here you can see a laser comes from this side, and by using some mirror and lenses, it goes to a polarizer beam, and then goes to this microscope. And then this is the device. This is a chip we integrate with the ROIC chip, and then we cool down the stage from 300 to 4K, and then shine light here. And as I said, with the time delay, we shine a probe laser by this path, and it connects here, and then goes to the device at the same at the gallium arsenide switch. So this is the part, as you can see, I'm standing here, this is the part is here, and this part is used for delaying this signal. And yeah, after connecting, we just cool down in, and we measure in vacuum stage, and we change the wavelength of the laser, 517, 780, and 1035, and we use often like in 280 femtosecond pulse duration. And we use lock-in amplifier and kit limiter uh, for the detection and for providing the voltage. But in this case, we are using zero voltage. So often, eventually it doesn't matter. We just put zero voltage, just connect with the kit limiter. And initially what we did is actually, so we just use a pump laser. We didn't use the probe one, just to mimic the previous reports. And indeed, edge photocurrent appears on the lower axis of our structure, and opposite photocurrent polarity appears on the electrode, which says this is just because of maybe photothermoelectric effect. But we are mostly interested on the edge part, what is happening on the lower symmetry. And next, we try with our own setup with a time domain photocurrent measurement, and what we see is very very fast signal from WTE2, which is around 180 to 250. If we change the position of the incident light, we can see this fast signal. But if we shine the light on the higher symmetries like A axis or B axis, we don't see any photocurrent signal. So we are confirmed that the ultra fast photocurrent is happening in WT2, and this is kind of a very very fast 250 0.25 terahertz at zero voltage, which is um, competitive to among other 2D materials. So there is only one report with graphene which is like 500 gigahertz level response, and they use some metamaterial structures. So we, if we integrate with other structure, metamaterial structure or quantum dots, then we can easily improve the signal. But now uh, the application part is finished. Now we can make this WT2 for fast signal photodetectors. But what is a mechanism? To understand that, we try to change the temperature of the cryostat from 300 to 4K. And by changing that, what we see is the photocurrent was initially Gaussian shape, and then by lowering the temperature, it becomes a peak with a deep shape. And that's kind of interesting. And to understand that, we compare with our pulse laser duration time, which is around 280 femtosecond, and it is very very slower than this pulse laser. Then we confirm this is because of the photothermoelectric effect, not because of the nonlinear one. Because for the nonlinear, which should have come within 1 picosecond or in femtosecond level. But why these two peaks come, that we try to understand. And then we change the incident power, and we see a linear power increasing, which is not the nonlinear case. We change the incident polarization angle, and by changing the left and right angle, the intensity was only changed, and nothing interesting was happening. And then we change the wavelength. So we cannot see any changes in the temporal graph of the photocurrent. So then we confirm that this is coming from PTE, and we try to understand why these two peaks come. And for that, RPIS, as I said, it's a very sophisticated quantum sensing technique. And for this material, RPIS study was previously reported, and it shows that by changing the temperature, the Fermi level of the material changes their position, the chemical potential changes. So around 40K for this material, electron pocket and hole pocket both were present. So when they change the temperature to 160, this chemical potential changes. And due to that change, around 160, this chemical potential hardly touches the valency band. And these physics can be imaged through this RPS measurement. And as a showed that around 160 to 280, the valency band is hardly touching the Fermi level, and that's why the whole pocket around higher temperature vanishes, sinks, and electron pocket expand. And we are also observing the second peak around 150K or 160K. This peak is absent after increasing the temperature, and roughly we can understand that this is coming because of different carrier dynamics of this material. So we calculate. This is kind of a tricky part and a little bit hard to understand because a lot of calculations are there. And so here we calculate the asymmetric Seebeck coefficient. So by taking care of a and b axis, we calculate SA and SP in separately, and then we are focusing on a minus b plane. Then we calculate SA minus SB, and then we calculate like the CVAC along SA and SB by taking care of three different condition, like when electron temperature is higher than the hole, when the isothermal case, when they have the equal temperature, and when electron is higher than the whole one. And compared to all these three, if we do SA minus SB just like simple math at 300K, then we can see that SA minus SB is positive for this condition and this condition. But when we have electron temperature higher than the whole, we can see Seebeck is flipping its sign. So then we confirm that due to this condition, the Seebeck is changing its polarity, and hence we are getting two peak for changes of the Seebeck coefficient. Anyway, so this is the just a confirmation from the theoretical perspective and understanding the physics. But we do really confirm that this is coming from the photothermoelectric effect, and this paper is under submission. And yeah, so we firstly, and we achieve very fast photo response from this WTE2, and we confirm it. And now we are trying to include with other material, like if we include WTE2 with black phosphorus, then we can have different photocurrent phenomena. And if we just make this kind of structure, like if we just tack and we shine a light on the heterostructure, then we can have many nonlinear photocurrent phenomena. As I explained, we are targeting for shift current. And now I will talk a little bit about Morse structures. What is Morse structure? If you throw a stone on some pond, then you can have a wave, right? And this, if you throw here and here, then this wave start to spread, and due to that, a wrinkle formed when they overlap each other. So the concept is, if you have a material and two material, or a same material with two layer, and if you change the interlayer angle, you can achieve this kind of structure. And at low temperature, at room temperature and low temperature, if you compare, if you shine the light, or you give some voltage, the electron will flow, right? And at low temperature, this electron can be trapped in this kind of Moire pattern. And on that pattern, you can really stop the, almost like stop the flow, and you can really reduce the scattering rate. And then if you study the superconducting phenomena or any other quantum computing applications phenomena, then you can understand a lot of superconducting thing happening in millikelvin range. So this Morse structure is also we can do for not only for quantum computers, but also for optical to electrical conversion. And graphene, of course, this is like the guinea pig material. Everyone start with graphene, and even for photodetectors, whether it's for photodetectors or quantum computers. So graphene was introduced with two different layers from MIT people, and they just have this kind of superconducting effect with different bilayer or tri-layer graphene. And similar way we can use it for, you know, for optical to electrical conversion. And so in this case, one report recently was published in Science, and they showed that if we use WAC2 and black phosphorus, and if we align them, if we stack them and align along the polar direction, we can break the symmetry. And due to that, we can achieve a Moire pattern, which is unlike the graphene one, but still, which is not honeycomb style or hexagonal style, but we can achieve a more structure, different structure. And if we shine the light along the polar direction, then we can have a photocurrent. But if we you know connect the electrode on different direction, which is the perpendicular direction of the polar direction, the photocurrent will absent. So this is a nonlinear effect because of nonlinear effect. And they increase the light, and they showed that for the for increasing the light, the photocurrent was increasing linearly fast, and then it was followed some other, 0.5, as you said, as you can see. So this is a nonlinear effect. And so they all this kind of experiment, they confirm that with these two material, not only graphene, but if you integrate other 2D materials, and if you stack it on some direction perpendicular parallel to the polar direction, then you can have a photocurrent along that direction, and it can follow the nonlinear shift current theory. And by using the machine learning, the other researchers, they can determine the angle, which angle is appropriate for the material to have the Moire structure, like WAC2 and MOS2. These people really did the DFT calculation, and they can determine the Moire structure for WAC2 maybe around 7.34 degree and MOS2 around 7.34 degree, and they calculated the band gap by using the DFT and MLFF, so which is the machine learning technique. And they compared those two values, and it matches. So it's really getting easier to have the Moire structure, because for experimental people, so we have to fabricate each angle stacking for the devices for each material. Then we can report, and then we can start the research, which will take a lot of time. So this kind of machine learning technique, if they calculate, and they can easily tell us that, yeah, within this angle you can have this kind of structure, and if you do this kind of application, and then we can have this kind of phenomena, it will be very easier, right? So yeah, and these people, they changes the angle like this, 4 degree to 30 degree, and they confirm that by changing this stacking angle, this photocurrent is getting vanished. And when the angle is around 30 degree, the photocurrent, almost like the BPV, the nonlinear photocurrent, was almost absent. So this is a technique we can follow, and we can do it with other materials or same material, not only WSC2 or BP. And we can improve the efficiencies like this way. And even if we have asterisk structures of electrodes, what we use in understanding what we do for quantum computers, like this kind of structure to measure the Hall effect. If we do the similar structure, and if we extract the signal from this electrode to this electrode, or this electrode to the perpendicular axis electrode, we can we can really image the photocurrent direction. And now if we change the so these are all these studies were done by DC photocurrent. There is no time domain report was done, not yet. So we are trying to report these kind of phenomena. Hopefully, we get something in future. And so these are the figure of merits for this kind of devices, which follows the nonlinear photocurrent phenomena. And they showed that the current density, which are being very, very high, if they compare with the nanotube. And it's so nanotube research are almost like 20 to 30 years, almost like very old. And these 2D materials are new techniques. They are achieving very good figure of merits compared to these nanotube applications, applicable devices. So yeah, so if we change the material stacking angle and the material itself, we can improve the efficiencies like this. We can have the detection from visible to the infrared. But as I said, for the infrared, not only very less materials are available, and it's not easy to um, detect a signal in infrared level, because you should have an infrared laser also to making this application. So yeah, I'll shift to nanocrystal. So now I will talk about the extrinsic part. And basically, this nanocrystal, what I studied for infrared imaging applications. And for infrared imaging, the thermal detectors, now currently we have third generation. And if we stack different infrared material and a capping layer, and then we integrate with the ROIC chip and FPA, then we can have this kind of application. But these materials, bulk, usually use bulk materials. And the detection range and the detectivity are like this. So we are interested on infrared one, not the visible one. Visible one, a lot of materials are available, but for infrared, mostly lead based or mercury based materials were there. And usually for this kind of detectors, normal photo detectors, like only active layer, or photodiode, like two different layer sandwiched active layer, or a photo FET, like transistors, often used. And photodiodes are theoretically, we all know that it's very fast. So if we use this photodiode, then we can have very fast signal. But the problem is, here people are using, for commercial purpose, a bulk semiconductor. And these are very bulky. And it influence high thermal effect due to heavy electronics. So somehow they are very costly, and we wants to reduce the cost. We wants to reduce the size, because as we are moving forward to microelectronics to nanoelectronics, so all we want in nano size, right? So we are trying to make very small devices which can which can have efficiencies compared to these commercial products at the same level. So recently, like 2023, this quantum dot colloidal quantum dot was recognized by Nobel community. And Mongiba Wendy was the one who did this quantum dots, who synthesized these quantum dots in his postdoc duration, like in 1980s or something. He is now in MIT, and he showed that by changing the quantum dot diameter, we can tune the application absorbance area. So if we change the band gap, the diameter, then we can change the band gap of the material. So the smaller the band gap, and you know the band gap, smaller the quantum dot size, band gap will be higher, inversely proportional. So like this way, metal, as we know that the conduction band and valency band crosses each other. But for bulk semiconductor, there is a band gap. But for QD, you can have a large band gap. And if you shine a light, then you can have a exciton, and that exciton will, after a certain point, after releasing that energy, and it will release by um, giving some emitting some light, and then you can extract that light, and you can apply for optoelectronics devices. And that's a thing. And so for this kind of community, often toxic material were used to make this kind of photo detectors or laser. So lasers are also very very costly, right? Like one femtosecond laser can be like more than 5 million or close to 1 crore. So if we want to reduce the size and the price, then we have to introduce some new phenomena, as I explained, and we should have some kind of new material, new generation technique, and new engineering to make the physics compatible to generate the photocurrent at that wavelength. And often these toxic materials were used. And here indium arsenide, lead based material, or mercury telluride, these all are non-toxic toxic materials. And mm, they got the Nobel Prize with these toxic materials. But we have to try some other materials like that can be used for human purpose, because it for toxic materials can spread a lot of cancers and all. So when you handle during the fabrication time, so you have to handle all these materials, and it's really dangerous. But
That,
if you have any kind of other, yeah,
hello,
yeah,
am I audible? Shosri sir,
yeah.
it's around 7:30, so we need
Oh,
to finish this session.
okay, okay.
Prior to that,
Sorry.
we'll be asking some questions from the audience.
Okay, okay.
Then we'll yeah,
I see,
close
I
the
see.
session.
Oh, I see. So can you give me 2 to 3 minutes? Then I can
Yeah, yeah,
finish it.
definitely, sir. Definitely, sir. We
Okay,
would
then
end the session within next 3 minutes.
okay, yeah, sure, sure, no problem. Sorry. So
No,
the
no,
talk
no,
was
no issue
about,
at all, sir. So, but we
yeah, yeah,
need to take some questions from audience, sir.
sure, sure, sure. So what we try to do, search some material, and indium antimonide is kind of a material which can have very fast, high mobility, and we synthesize this material with very small sizes. And then um, I'll move to the application part. So what we did is we really fabricate this indium antimonide quantum dot, and we improve the quality of the material, and then we made the photodiode. And by making that at 0 voltage, we can see the photocurrent was generated, and the speed was unfortunately very low. And but at 0 voltage, the main important point was at 0 voltage the photocurrent was achieved. And if we change the incident light, then we can have very nice features of the photodiode. And the main motivation was to reduce the dark current of these devices. And we change some chemical process, and then we optimize the material product quality, and then we improve the efficiencies of the material, and we reduce the dark current. And then we compared the commercial products from Hamamatsu Photonics, which is very known for making this photon detector, single photon detector, this kind of devices. And we really see comparable region comparable values with this our technique, our material. And yeah, and if we use these devices and integrate with the ROIC chip, then we can make this kind of infrared cameras. And if we shine the light on a dark field, then you can see, in the dark field you can see the photograph easily. And if you integrate with AI with this imaging technique, you can really improve the quality of the image. So this is the raw image just before the optimization enhancement of the image. And if you use some class A or some other technique, then you can improve the quality of the imaging. That's other application. um, that's the other field was focused anyway. So so yeah, I already explained about the 2D material application and how we can improve the efficiencies and how we can improve the quality of the flakes by using the AI, and by also the moire structures, which are really new engineered nanocrystals. It's really tough to understand in which angle this moire will appear for the new material. So in this case, this machine learning technique can be very, very useful. And for the nanocrystal, also for the imaging purpose, it can be new technique, and it can reduce the cost. And yeah, thank you very much for attention. And if someone needs any question, or some information about some paper or some question, please email me also. It will be easier to answer, because yeah,
So we'll
because
be
already
Thank you.
we'll provide your email to the participants so that they can
that will
send you
be
mail.
Let
yeah.
me communicate with
Yeah.
you. Many
Yeah, sure,
thanks
sure.
for very interesting and wonderful session.
Thank you.
With this,
We would like to finish this session. Any question from the participant? We can take one question only, since time is very constrained. The second session will be started from 7:30. Scheduled time. Yeah.
Yeah, okay, please just send me an
So
email.
let us.
Yeah, send me an email if someone has any
Okay, so
question.
let us finish
Yeah.
this session. And,
Yeah.
thank you very much for your wonderful session.
Thank you
Dear
very much
participant,
for having
kindly
me.
join, read this link and join the session 10 link.
link of session 10 is already shared in the WhatsApp group, also mailed to you. So we are closing the session. Thank you very much, Dr. Chatterjee. We are closing the session.
Thank you very much for having me. Thanks a lot.
Okay.